Welcome, everybody. We are the Canadian Society of Iranian Engineers and Architects. We are a non-for-profit organization and trying to help our colleagues in professional and cultural issues. And we have a lot of gatherings, technical gatherings like this one, and celebrations like Nowruz and Yalda. And this presentation tonight is conducted by the civil group of our society, which is called Nondestructive. Please, Mr. Ahmadinejad, begin the session by introducing our valued speaker, Dr. Faraz Massoumi.
Thank you, Darafshin. I don't want to take up any of your time, so I'm just going to start and introduce our valued speaker. It's really my pleasure to introduce our today's speaker, Dr. Faraz Massoumi, a professional engineer. Dr. Massoumi is a dedicated bridge engineer with over 19 years of experience in design, rehabilitation, and inspection of bridge and culverts. Dr. Massoumi holds a PhD in engineering science from the Middle East Technical University of Turkey. His notable contribution to the field include playing a pivotal role in developing the Turkish bridge management system for the Ministry of Transportation of Turkey in 2012. His expertise extends to conducting detailed condition surveys, OSIM inspections, enhanced inspection, drone inspection, and non-destructive testing on more than 1,200 bridges, both in Canada and overseas. Currently, Dr. Massoumi is making significant contribution to the City of Toronto Bridge and Structures Department within the Asset Management Group. Dr. Massoumi has published several journal and conference papers on bridge and management systems and bridge engineering. Notably, he was honored with the Best Paper Award at the Second International Conference on Civil Engineering and Architecture in Barcelona, Spain in 2013. So I'm going to ask you, everyone, join me to welcoming Dr. Massoumi to start his presentation and benefit from it. Dr. Massoumi, please.
Okay, thank you so much, Maya, for introduction. Hello, everyone. So let me share my screen then. Can you see my screen?
Yes.
Yes, we have it.
Okay. Hello and good evening, everyone. In this presentation, I will try to give you a brief introduction to bridge management systems, the reason that we need bridge management system, the way that they work. I'm going to show what is the input and output of a BMS. And I'm also going to talk about bridge inspection, some applications of non-destructive testings on bridges. I hope you enjoyed this presentation. Okay, the content of the presentation, the first item is about my PhD studies and an R&D project that I worked on. And the output of the project was KYS, a new bridge management system for Ministry of Transportation of Turkey. The second item would be the demo of that BMS. The BMS was developed back in 2012. And the third item will be, I will go through an RFI for government of Nova Scotia, and I will briefly show new platforms for development of BMS. The fourth item would be highlight from some interesting bridge inspections that I have had, and finally questions and answers. Okay, the first part of the presentation is about development of KYS. Turkish bridge management system. During my PhD studies, I worked about 3 years on an R&D project from beginning to the end. And during these 3 years, we developed a BMS from scratch. So the project was a national research project, and the scope of the project was development of BMS for Ministry of Transportation of Turkey. You can see some general information about the project, like project duration, 2.5 years, budget about 1.1 million US dollar, the start date, the end date, so on and so forth. The organization of our R&D project is shown here. You can see Ministry of Transportation as the client, our university, and TÜBİTAK as research body, and software development company that was supporting us in applying our ideas in the software. The academic group consisted of 7 professors, got involved on this project. The project ran by my PhD supervisor, Professor Akgul, and other professors supported us in that project. The factors that initiated the project, like river effects, environmental effects, and etc. Unfortunately, a couple of years earlier than this project, a bridge was collapsed in southeast of Turkey. And if I'm not wrong, about 11 people were killed on that incident. And it was the main reason for initiation of this national project. The project scope was software development, establishment of inspection damage categories, collection of visual inspection data for 200 bridges as pilot group of bridges, and application of non-destructive testing or NDT on 10 bridges. We divided the whole project to 4 work packages, as you see here, work packages 1, 2, 3, and 4. And here you can see a Gantt chart for project phase 4. We had a bridge inspection seminar for training of our engineers, because we hired 4 engineers to do the inspections. And this basically seminar was to train them. This was actually held in 2010. And we had another training session for NDT inspections. The NDT devices were bought from a US manufacturer, James Instruments. And moving forward, I will show you the NDT devices that we use for this project. We had a health and safety training for bridge inspectors and bridge inspections, and the bridge inspection manual that we developed for ministry. We have very similar manual here in Ontario. We call it OSIM manual. And now I'm going to show you some snapshots of interface of the software that we developed. KYS, this is the first, the snapshot, is a web-based BMS. You can see the BMS website here. I will show you the BMS demo that I prepared before the delivery and handing over of the project for ministry. And here you can see the startup screen on KYS with 6 modules on the left side. The modules were definitions, inventory management, inspection, cost, planning, and reporting modules. This one is the inventory management module, very similar to MTO's new version of BMS, which developed by Sixense recently. All information about bridges goes here. And as you see on top, there are 5 tabs, including bridge inventory data, elements, inventory card photos, and even projects. You could upload as-built drawings and any reports that you have for individual bridges in this module. This one is inspection module. All information related to the inspections goes here. These inspections could be both visual inspection and non-destructive inspections. So basically, when inspectors go to the site, they measure the deficiencies and enter all information to this module. The pilot bridge group, basically here you can see the black dots on the map. This is a map of Turkey, and it shows the location of 200 bridges around 3 big cities of Ankara, Istanbul, and Izmir that we inspected and entered to the BMS. Basically, we developed the BMS to ministry, and we inspected 200 bridges as pilot group, and we entered all those information to BMS to run the project, to run basically the software. And after that, and they were going to do their inspection. They have about 6,000 bridges and manage their bridges by that software. Here is the cost module based on the unit cost that we got from the ministry, unit cost for repairs. And we use those repair costs in this module. And here you can see the transition probability matrix tab that I will discuss in planning module. These numbers are very, very important for bridge management system. These are the percentages. Now here, planning module. The most important module that we had in KYS was planning module. This module gives the bridge owner the capacity and capability of spending their repair and rehab budget in an optimal way, and have an automatic system to consider different scenarios to repair and rehabilitation and even replacement of the bridges. Basically, the system helps bridge owners to make decisions, and this planning module has two tabs, two subsections of optimization and ranking tabs that I'm going to elaborate more here. First, subsection is optimization. I need to do some explanation here. For each bridge management system, we have a terminology of conditional state. As you see here, definition of conditional states for each damage type: condition state 1, 2, 3, or 4. Condition state 1 means there's no damage. It's like brand new bridge or brand new element. And bridge condition state or condition state element of 4 means critical amount of damage. And there are possible damage types for each element. For example, here you see possible damage types for reinforced concrete beam, like cracks, deformation, exposure of reinforcement, delamination, dents and pits. And also definition for each condition state. For example, for crack, the damage type of crack for concrete elements, condition state means there's no crack. Condition state 4 means the width of the crack is more than like 3 millimeter. And these are the definitions that you need to have in each BMS. And then we introduced two factors of maximum impact factor, MIF here, which shows the importance of an element and damage type, and distribution factor, which shows the distribution of damage types in different condition states. Based on these factors, condition state weights are calculated, and it leads us to calculation of bridge condition index. Bridge condition index is basically a number which shows the condition of the bridge. Here you can see the way that bridge condition index is calculated in OSIM manual in Ontario. This one is completely different than what we had in KYS. Here you see, for example, bridge condition index is 73 for this bridge. If the bridge condition index is more than 70, we consider it as a good. If it is between 40 to 70 is fair, and if it is less than 40, it is in poor condition. You see here a simple curve, but this curve is very important in optimization and decision-making process of bridges. We call this curve as performance curve. The horizontal axis here shows the age of bridges, and the vertical axis shows BCI or bridge condition index of the bridge. This curve is not just for one bridge, it's for all bridges in one category of a bridge. For example, we have one curve for all precast girder bridge, one for box girder bridges, one for arch bridges, and so on and so forth. This curve shows basically the deterioration of BCI from new bridge to a critically damaged bridge. And when the bridge is aging, the BCI of the bridge goes down. And if we repair the bridge, like here you see the like point A, it goes up, and it deteriorates, it goes down, and repair in another repair. Where we replace it in point B, it goes back to 4 and it deteriorates again. So that's the normal behavior of the bridge. And also, it's very important to have previous inspection records to create these curves for bridges. Now the question is, how we are going to use these curves. Here is a matrix that we call it transition probability matrix, or TPM as a short form. We calculate this matrix by using the performance curve that I showed you in previous slide. In this matrix, P11 here means the probability of transition from condition state 1 to condition state 1 in 1 year. Basically, it means it doesn't change and it stays in same condition state. P12 means probability of transition from condition state 1 to 2 in 1 year, and so on. In top right side, you can see a simpler form of these TPM metrics, and some of the components of these metrics are 0, because it's very unlikely that the conditional state of the breach or element goes down from, for example, 1 to 3 or 4 in 1 year. And these graphs basically here show TPM in a simpler way. These are the probability that it goes from, for example, 1 to 1. It means that 93% it stays in condition state 1, and 6.16% it goes to condition state 2, and same here. And here, this one is, you see here, A0 is a do nothing. If we do nothing, it happens like this. But if we do repair work, it goes up. It means it can go from condition state to condition state 1, or even from condition state 4 to 1, if we repair or replace it. Here is a performance curve for one breach type, and I calculated the transition probability matrix for this breach type in right bottom side by solving this optimization equation on top right here. And now you can see how we can use this transition probability matrix for prediction of BCIs in future. As you see here, Q0 is initial BCI or current BCI of a breach. And if we multiply it by TPM, it gives us BCI after 1 year. Here, Q1. And if we multiply the initial BCI with TPM 3 times, it gives us the BCI after 3 years, and so on. So if we have the transition probability matrix here, based on the performance curves, and we have the conditional state of a breach or conditional state of an element, we can easily calculate like what would be the conditional state of the breach in 10 years after by multiplying 10 times in TPM. And then the matrix is being used in this linear programming formula for solving the optimization problem. These optimization problems is based on Markov decision chains. And the output here would be the selection of do nothing or repair action based on the optimum path that the system would select for us. Basically, the system considers repair or do nothing actions, their cost, how much the repair action going to improve conditional state of the breach, and what will happen if we postpone the repair of the budget, the repair of the breach until higher conditional state. The breach management system considers all these options and then selects the optimum way of spending available repair. And that is the whole ultimate goal of breach management system. Why we need breach management system? Because we always have thousands of breaches and we have limited budget. We want to see how we can spend that limited budget in an optimum way. Here you can see the Fortran source code that we developed for this purpose. This Fortran code solves the optimization formula that I just showed you. And the code, the Fortran code was embedded to the software, the web-based software that we had. And here is the output of the BMS software. Here you can see the check marks here. And these are, for example, these information are all for one breach, and this is one breach, another breach, and these are the elements here. And if there's a check mark here, it means that basically the BMS recommends to repair that. And if there is no check mark, it means that the BMS recommend to do nothing for that element. And here on the right side, here you see we have an override system. So basically, after the BMS runs, the bridge owner, bridge engineers can override the system by selecting these options. And it helps very much because sometimes the contractor is already there and you prefer to do the other elements that the BMS didn't select. And then the prioritization subsection of the optimization module. For prioritization tab, we use this formula that we call it multi-criteria prioritization formula. After we run the optimization program, we can run the prioritization program. In this tab, the BMS helps you to make decision to spend your budget between group of bridges. The three factors that we used was BCI, maintenance costs, and average daily traffic. And these are the WIs, are the multipliers that we can set for each run. And basically the total of these WIs should be 1. And here you can see the result of the ranking program for 10 bridges with equal weights for those three factors. Here you can see you enter the budget here, you select the bridges. You can see the different rounds that we have for 200 bridges, 100 bridges, 20. You can select whatever that we want and enter the budget for your repair and replacement work, rehabilitation program, and set these criteria and run the program. And the program tells you select which bridges, and in each bridge select repair which elements. Reporting module here that is creating all reports in the PDF format. And then the system administration module for access purposes. And then after we developed the BMS and we inspected 200 bridges, after we entered all information to the BMS, we selected 10 bridges to do the NDT, non-destructive testings on those bridges. And you can see here those 10 bridges in red circles and the location of the bridges that we conducted our non-destructive testings. The first device, we had 4 devices for non-destructive testings. The first device is Windsor pin. The Windsor pin is a system basically that uses a spring-loaded device to basically push a steel pin into the concrete, and the depth of the penetration of the needle or the pin correlates to the compressive strength of the material under the test, and it measures the compressive strength of the concrete, and it's very similar to Schmidt hammer that I think most of us are familiar with that. And here you can see application of Windsor pin on girder of a bridge. This guy is me when I was very young back in 2010, applying this Windsor pin on girder. And the second device was Armeter 3. That this device is a rebar locator, basically to locate rebar, conduit, pipe, or anything metallic object in concrete. For some tests, it's essential to locate the rebars beforehand. For example, for previous device, for Windsor pin, we had to locate rebars first and then apply the pin away from the rebar location because it would affect the results of basically the compressive strength of the concrete. And here is the application of this device on the soffit of a bridge. And here I show you the access equipment that we use. This is an underbridge platform. I used a very similar platform here in Ontario for fatigue inspection of a Windy Point Bridge in Thunder Bay that I'm going to show you some pictures. And I want to basically emphasize that for bridge inspections, NDT, those kind of things, fatigue inspection, the access is one of the important factors. This device is G-Core 8, which measures the corrosion rate of rebar in reinforced concrete elements. And this device is very similar to what we have in Ontario, which we do in detailed condition surveys. We call it half-cell potential test. Here is the application of the device on bridge. And this device is an ultrasonic device that we use for estimation of concrete strengths. This entity device is very helpful for concrete and strength calculation, and also calculate the crack depths in concrete. I use this entity device for another MTO project in Anderson Bridge, close to Kenora in Ontario. Basically, I will show more information for this device in moving forward. Here you can see how it works. It has two probes, one sender or transmitter and one receiver. Based on the distance between probes and travel time, it measures the velocity of wave in concrete and correlate it with compression strength of concrete. If there is any void or delamination inside concrete, it basically reduces the velocity of the wave. Can you guys hear me well?
Yes, it's clear.
Okay. Okay, so I use this device, this ultrasonic pulse velocity device in Anderson Bridge, and after that, basically it was an MTO project, and after we did the inspection and wrote the report, engineering report, I wrote a paper, and I published a paper, and I want to show you here the application in real world. This is the Anderson Bridge. This bridge had longitudinal cracks on the bottom flange of girders. And MTO was curious and kind of worried about to see these longitudinal cracks all over the length of the bridge. And the main concern was to see if debonding has happened on the strength, because these girders was pre-stress girders. And they plan for major rehabilitation of this bridge, and they just want to know about the debonding, because they want to know that the deck replacement would suffice, or they need to replace the girders as well. Here you see the device that we use, very similar to what we had in BMS in KYS. And also we use the GPR, ground penetrating rod radar, to investigate the bonding for this entity inspection. And here you can see the formula to measure depths of crack by using UPV. You see two probes. You need to put probes on two sides of the crack, and using this formula, you can calculate the depth of crack. And I'm not sure if you can see this picture clearly, but this picture shows the depth of crack on about 25 locations. Here you can see this side is west abutment, this is the east abutment, in the middle is pier, and these are the girders. And we did the measurements on about 25 locations. And here on each location, you see the depth of crack, like 43 millimeters, 50 millimeters, 61 millimeter. And you can see that the cover of the basically rebars were much more than these depth of cracks. And we also analyzed our scans from GPR, and we concluded that debonding hadn't happened on girders of the bridge. Okay, here I'm going to show you the demo of the KYS that we developed. Before the delivery of the project to the ministry, I made this demo of this BMS, because after delivery, we didn't have access to the BMS. Okay, so for example, these are the videos. I hope you can see this smoothly. This one is inventory management module. All information about the bridges are here. The elements here, inventory cards, and the pictures, projects. I move a little bit forward. Oh, sorry. Yeah, these are the elements for each bridge. And these are very interesting, very old-fashioned hand sketches from like 6 years ago for these bridges, like 70 years ago, 80 years. We even scanned those information and put it here. And here are pictures for each bridge, like 25 bridges, 25 pictures for each bridge. Yeah, this one was inventory. The language of the BMS was in Turkish, but the snapshots that I show you was in English because I put all those information in my thesis and it has to be in English, but these are all in Turkish language, the language here. And this one is the inspection module. All inspection information goes here. Basically, when you go to site, you do inspections and put everything here. All deficiencies in percentages. And the next slide is, this slide is planning module, transition probability matrices that I show you. Or here, these are the transition probability matrices. And here you can see the output of the optimization for this bridge. You see some of them are selected, some of them are not selected. And different tests that we did, 200 bridges, the maximum that we had, but you could easily do for 1,000, 2,000 bridges. And okay, here I'm going to show you an RFI for bridge asset management software for government of Nova Scotia. The reason that I show here is the new platforms that are for BMS. Here, in 2020, when I was in my previous job, I came across with an RFI for government of Nova Scotia about development of bridge asset management software, and I thought I can do that. And I created a team, and we basically group up with a digital company in US to prepare a solution. And here you see the RFI page and the table that there were about 100 requirements in format of a table here that basically they needed for their solution. We presented our solution into 2021 and they liked it, and they said that they would issue RFP in future and asked us to send them our proposal and detailed costs on that time. So after that, I moved to City of Toronto, and I don't know what happened to that project. But this is a team that we created, and basically the presentation that we did. And here you can see the models. The important thing here is the cartograph. Cartograph is a platform that you can do anything that you want. I mean, for the engineering perspective, you can see different applications for different cities that they had. Application of these platforms in infrastructure are shown here, and basically can be used in all kind of asset management, like transportation, parks, water utilities, flood management. And as I mentioned, the reason that I show here, that these new developments in tech and software engineering can make it much easier and more effective to have systems like bridge management systems. These platforms are cloud-based, and you have much more flexibility in doing modifications for different purposes. And it can be on bridge management system or any asset management system. Okay, and it's very important bridge management system is very important, but to be able to maintain your bridges in good condition, a good BMS is not enough, and good inspections are also required. Here I'm going to show you some interesting pictures from my previous inspections. I hope you like it. So this is the first one. This one is enhanced OSIM inspection that I did for a Baskel Bridge on St. Lawrence Seaway on the Welland Canal in Niagara, St. Catherine. For substructure, I use a bridge master. This device is a bridge master, which gives access to you for underside of a bridge. And we just have 2 of these bridge masters in whole Ontario. And although they are their hourly rates are very expensive, but they are very useful for some special cases, because you can have different kind of rotations and you can easily reach everywhere underneath of bridge. And this canal is also very interesting. I'm going to show you another video at the end, and I give you more information. This is the same bridge, and the lower part, the substructure, we use bridge master, and for superstructure we use cherry picker. This bridge is they call it Bridge 1 because I think it's the first bridge from the north, if I'm not wrong. And one of the important, interesting thing here is they have hydraulic gates on this canal, and they pump water to basically 2 sides of that gates to change the water level for transportation of cargo ships between US and Canada. And it's very unique infrastructure in Canada. This is another bridge. This one is Matagami River Bridge in Timmins in northern Ontario. That I did bridge condition survey, detailed bridge condition survey and drone inspection in summer. Here is another view of the bridge. You can see our crew was working here for detailed condition survey. And because of the shape of this bridge, the configuration, we couldn't do the inspection underneath by bridge master because of these truss members. So this is the way that we did inspection. We did this inspection in winter in minus 40 degrees by walking on the ice here underneath of the bridge. Basically the health and safety protocols for inspection of the bridge by walking on ice is a little bit complicated. This one is another bridge, Windy Point Bridge in Thunder Bay, which I did fatigue inspection for this bridge. The total length, it was a very huge bridge. The total length of the bridge was 144 meters. And I took this picture very far away, so it was a very big bridge. And here you see the fatigue inspection, and we did this inspection just in beginning of COVID. And as you see, we used a very similar platform that we used back in my PhD project. And because of the shape of this bridge and number of girders and bays here, this platform, the access platform, under bridge platform, was much faster than Bridge Master. Because 4 people could basically stand on this platform and do the inspection at the same time. And we basically hired we rented this platform from Quebec. It wasn't available in Ontario that time. And this is a crew that we had. It was the beginning of COVID. We had to have physical distancing, and it was making our inspection more difficult. Some interesting pictures of the bridge. You can see bearing of this bridge, the corroded bearing on the west side of the bridge. And here, even more interesting picture of the bearing on the east side of the bridge. Here you see the roller bearing type, and you can see where the roller is landed. Basically, it's not under the bridge. Okay, and this one is, I didn't inspect this bridge. Let me run the video, and I can talk on it. So yeah, I haven't inspected this bridge, but I was there for a pre-bid meeting, and I captured this movie, and it really shows how interesting is our field as civil engineers. This is the Veland Canal. So here are the gates you see here, and it was a very huge cargo ship that just passed. And this bridge was a bascule bridge for railway bridge for trains. So this Veland Canal, they have 8 gates here. If this is one of them, they have 8 gates all over the length of the canal. And the large cargo ships in length of about 200 meters goes on this canal, and it basically connects Lake Ontario to Lake Erie. And it was very interesting. And basically, they close these gates and they pump water to other side and lower or actually lift bridges on 2 sides of the bridge, on 2 sides of the gate. And for moving under this bridge, it has to be doing a harmony. So basically, they open the bridge and then they lower the water level. It takes 11 minutes for them to basically pump the water. They pump about 20 million gallons of water. And you see here, it goes back to normal condition. And then you'll see that the gates close. And basically, it was catwalk on those gates that we walked over that gate. These are the gates. And for these bridges, the inspection of these bridges is more complicated because they have different components, like they have structure, mechanical room, electrical portion of the bridge. And for these inspections, you have to have those engineers, I mean, mechanical engineers, electrical engineers, and structural engineers. Okay, so it was my presentation. I hope you enjoy it. And if you have any question, please feel free to ask. Thank you.
Thank you, Dr. Mastrumi. We really enjoyed the presentation. Was really beneficial, informative, and of course practical. Thank you so much. And everyone, if you have any question, please feel free to put your comments.
Hello.
Hey.
آقای فرزین.
Yeah. Could you please, first of all, thank you for your presentation. Could you please give us some references for fundamental aspects of calculations for bridge management system?
You mean the optimization or which part of it?
Everything you think an engineer needs for this bridge management system.
The most important part of it is optimization. I even took a course in my PhD, even after I passed all my courses as elective course, because it was the most component or most important module is the optimization module. So it's very important to have a good grasp of optimization, how it works, basically what is the objective function, which constraints do you have. That is most important part. And then also understanding the deficiencies, like first of all, you need to know bridges very well, which elements are there, and what are the deficiencies. Your question is a little bit tricky. I don't know. You mean in which perspective? I mean, developing a BMS or using BMS? If you want to,
Actually, development of BMS and especially statistical part.
yeah, the development is more complicated, of course. So it took 3 years for us. We were a group of like 15 people. So uh, first of all, you need to categorize your deficiencies, the condition states, how conditional state of an element is going to be calculated from conditional state of deficiencies, because each deficiency has different conditional state. And then how you are going to calculate conditional state of bridge from conditional state of elements. So let me show you here, for example. I didn't go through this slide in detail. I can talk about this now. The way that we calculate bridge condition indexes in Ontario is completely different. Here, for example, you see these are the elements, the abutment, the element group. These are element groups, and elements are here. So you have the unit of each element, and the unit price for each element. For each bridge, you have total element quantity. For example, 318 square meter of abutment wall. And then if you multiply this number to the unit price, it gives you the total replacement value of that element. So it means that if you want to build an abutment wall, with this quantity, it costs this amount for you. And then you have the inspection records here. So you have excellent, good, fair, and poor elements. If an element is in poor condition, it has no value. So the multiplier is 0. If it is fair, it is 0.4. It means if you have like 100 square meter of fair abutment wall, you have to multiply by 0.4. You have almost 40% value there. And if it is good, 0.75. And if it is element, you have 100%. So you multiply these numbers and you have the current replacement value. So it shows the current value of the bridge. And if you divide this number to this number, it gives you the element condition index out of 100. So you have condition index of elements for all elements, and then you take average and you get the condition index of bridge. So if you want to develop your bridge management system, you need to know how you are going to calculate these condition index. For example, I can give you some information about the best or most sophisticated bridge management system in the world, which is Pontis, is US bridge management system. And in Pontis, there are 9 condition states. Here we have 4. So in Pontis, there are 9, and you need to know how you are going to calculate these condition index. And in that case, your transition probability matrices are going to be 9 by 9, more complicated. Yeah, those are basically the base of the bridge management system. And then you need to know how the cost is going to work with the repair, and how you are going to use the cost in optimization. It's a little bit complicated. Yeah, it's very difficult to reply here,
Yeah.
but for example, my thesis is open source. If you want, I can share with you, and you can get
I appreciate it if you shared your thesis.
yeah,
And
definitely,
also, I
absolutely.
have another request. I think a few slides later.
I can hear now.
You have some matrices for some calculations. Uh, I want a reference for these matrices.
Sorry, I lost you for a second. So can you repeat your question again?
Yeah, I'm looking for the reference for calculation of the matrices you used in these calculations.
Okay. Yeah. If I share my basically thesis, everything is there.
Okay,
Yeah.
perfect.
This one is, let me show you this formula. Basically, this is a formula
Yeah.
that is based on Markov chain. This is a statistical approach. It can be used in anything. That's the Markov chain model. I can basically share with you.
Okay, thank you very much.
Yeah, my email address is fraz.mansumi@yahoo.com, or even you can text me in LinkedIn or whatever works better for you.
Okay, thank you very much.
No problem.
Thank you. Dear Afshin, you raised your hand. Do you have any question?
Yes, I would like to thank Dr. Masumi for a very comprehensive and informative presentation. I learned a lot. And my question is about different types of inspection. How often do you prescribe, or is there any rules that you are following for routine, or sometimes we call it screening inspections? And when is the time for a deep inspection? And also, if you would like to continue for proof inspection, I would appreciate those. And if you want to discontinue your screen share, that would be all right.
Okay. I just maybe someone asked question. I want to show his formulas or something, but yeah, I can stop sharing. Yeah. Okay. Yeah, it's a very good question. First of all, in Ontario, we have OSIM manual, Ontario Structure Inspection Manual, which outlines the guidelines for inspections. Normally, all bridges should be inspected visually every other year. So we have biennial inspections. So all bridges should be inspected every other year. But some bridges are that basically the OSIM reports calculate the bridge condition index, and if it is less than 70, it means that they are in fair condition or poor condition. You need to inspect more, and we have enhanced OSIM inspection. For regular OSIM inspection, basically the inspectors need to hammer sand concrete everywhere that reach the hand, I mean the accessible areas like abutments, anywhere that they can reach. But for enhanced OSIM, they need to hammer sand everywhere, basically. And here in Canada, the biggest problem is delamination because of the salting that we use during the winter. That salt goes to concrete and basically goes to the rebar, reach to the rebar level and corrode the rebar. And after the rebar is corroded, it increases the volume of the rebar there, and it pushes the concrete and it makes crack, and eventually it changed to delamination and then spalt, and it reduced the strength of the concrete. So we have then enhanced OSIM inspection, and then case by case, for example, for steel bridges, like for bridges over 30 years, you have to do fatigue inspections every 5 years. There are different, scenarios for different bridges, but normal regulations every 2 years.
So if I may continue, you mentioned different types of non-destructive tests. I want to ask about accuracy and reliability of those tests, and I guess those would be okay for the regular inspection and screening inspection. But whenever you go deeper and want to investigate actual status of the bridge, how much can we rely on non-destructive tests, and when would be prescribed to go into standard tests of ASTM, etc.?
Okay, so if I want to circle back to your first question, we also have detailed condition surveys. So basically, every 5 years, normally we do detailed condition surveys on bridges, and that's kind of destructive testing because we get core sound samples on bridges, and then we have the bridge detailed condition survey report that the rehab design is done by using that report. And in that, for example, detailed condition survey, we have non-destructive testing of half cell potential test, which basically corrosion potential of the rebar is defined by that test. And there are some tests that, I mean, there are always, I mean, there's a fight between people that some people that they think non-destructive testing is very useful. Some people they don't believe, but it depends on the situation and it depends on the basically knowledge of the inspector, and case by case is different. And because you know you don't take core or you don't see exactly what happens. Everything is based on the estimation, based on the everything is based on the very objective, you know, it's very objective, and definitely it's very helpful. For example, I know that MTO is looking into options of adding GPR testing to detailed condition survey now, because it's very useful. You can scan the bridge deck, and sometimes even you can see the corrosion of the rebar and the lamination. Yeah, there's no, I mean, yes or no answer to that question. It differs from case by case, but it's very convenient, you know. For example, sometimes you need to do destructive testing, but it's very expensive. It's very, as you see, it's destructive, but non-destructive testing is easy, cheaper, and sometimes you can get much faster result. Yeah. I hope I answered your question.
How do you feel about combining these two and actually calibrating non-destructive tests with standard tests? For example, in my experience, sometimes we took one core sample from the abutment and did the non-destructive test right there and correlated them. And then we used that correlation for hundreds of other non-destructive tests that we did. What do you think about that kind of calibration?
I think that is the ideal case. I mean, if we can do this, that is the ideal case. I mean, that's the best way of doing that inspection.
Thank you.
No problem.
Thank you, Dr. Masumi. Everyone, you raise your hands, please.
Hi, Dr. Faraz. Thank you so much for the excellent presentation. I really enjoyed it. My question is about the nuts and bolts and the roller bearing you actually showed in one of your slides that they look pretty rusty to me. And so I was just wondering, like, when do you basically know when to replace those nuts and bolts or bearings when they have corrosion on them?
There are different types of bearings, and for some of them, the corrosion is very important, like the roller type of bridge, the bearings. It's very important to see first of all, you need to inspect those bridges twice a year, once during the winter and once during the summer, because it rotates and you can see the rotation, and you need to basically measure there's angle and record it. And sometimes the corrosion basically prevent the rotation. In that case, you need to replace it. And that's the designer work. Basically, the designers take a look to detailed condition survey or the enhanced inspection reports, and they decide. But normally, whenever the corrosion make it difficult for bridge to rotate, the replace it. Right now, there's a bridge in Eastern Adelaide on DVP. There's a very long bridge. Right now, we have a project in City of Toronto to replace those bearings because we had the same problem there, basically because of the corrosion, and it was making difficult for rotation. And when that corrosion prevent from rotation, it create another stress somewhere else. So that's not good for bridge.
Oh, okay. So it's only in the case that, it prevents like the movement of the bridge. So is it possible to know beforehand, like, when to, well, I know that from the looks of, the metal parts, they look rusted, the surface is actually rusted, right? But
Yeah.
I'm actually a mechanical engineer. I'm not a civil engineer, right? So like I know that, the metals, like, the rust, and there's like, there's a stress and tension on them. So there's like a yield point, and they're going to break, right? So how do you basically inspect them, like, without removing them and knowing, like, when is actually, well, you said, like, it actually prevents them from like moving the bridge. But like, before actually we get to that stage that, that we need to, well, it's necessary to replace it, like how to do it
Yeah.
beforehand.
Yeah, for other bearings like elastometric bearing, it's not a big deal, those corrosion. But to answer to your question, for example, for Windy Point Bridge that I showed you, the corroded bearings, we did fatigue inspections on them, and there is a non-destructive testing to measure section loss on steel. Basically, there's an ultrasonic test. There are three types of non-destructive testing. One is ultrasonic. There are two others. I forgot the name, but I forgot. But basically, they measure the section loss by non-destructive testing, and if it is, for example, more than 10% section loss, you need to replace. So you don't need to open anything. You just do by ultrasound. Yeah, the other one is dye penetrant. So dye penetrant is for identifying cracks on steel. Basically, it's like a spray. They dye, and you can see the crack, if any. But the section loss is with ultrasound. They have a device that calculates the section loss of steel.
Oh, okay. Alrighty. Thank you so much.
No problem.
Thank you. Anyone else has any question or comments?
Okay, Mariam, I guess we can wrap it up right here.
Yeah, okay. So I wanna say thank you, dear Dr. Masni, for your presentation. I'm gonna say thank you to everyone to contribute to this session, and everything was fine, everything was perfect. Thank you so much, and have a good night.